Welcome back, my structural analysis friends. In this lesson, we're going to be studying yet another approximate method that is useful for lateral loads on tall, flexible buildings. This method is known as the cantilever method or the beam analogy method. So without further ado, let's get started. The cantilever method is another approximate technique that is useful for structures that are subjected to only lateral loads. It was developed in 1908 by A.C. Wilson and is appropriate for tall, flexible building systems. And basically the idea behind this method is that under lateral loads, tall building frames behave like cantilever beams. And you can kind of see that if you picture a building, something kind of like this, where this is the foundation, every beam or every building on the planet is a cantilever structure of some sort. All I have to do is turn it this way, and it looks exactly like a cantilever beam subjected to some sort of load. And we know that this building would then flex, something like what you would expect a cantilever beam to do. Okay, the part that we also see that happens is that we get a portion of the columns that are put into tension, which would be these upper ones, and then a portion of the columns get put into compression. And depending on how these are arranged, we can start to make some assumptions. So first thing that we're going to do is that we're going to kind of go back and look at our basic beam analogy and say that the axial stress in a beam, if you remember our rectangular cross-section, when we looked at it, when we calculated the stress, we knew that we had a neutral axis that for a rectangular section was somewhere in the middle, okay, and that corresponded to a strain of 0, which then corresponded to a stress of 0 at the neutral axis location, and that my largest stresses in a beam subjected to flexure were at either the top or the bottom, okay, and we found those amounts by doing MC over I for the top, where C is the C top from the distance from the neutral axis up, and for the bottom it was MC times the bottom times I. Now again, for a positive moment, we know that the beam goes into tension on the top, compression on the top and tension on the bottom. And we're not really worried about that in this particular example, but we know that the lesson to take out of this is that we know that the relationship by this function was linear, okay, and that the highest values occurred at the ends of the beam. So if we kind of look at what's happening in our analogy of this beam, that's kind of what we're seeing here. That here in the middle, near the neutral axis, we were getting very little axial load in the columns. Okay, but out at the end, I got my maximum tension, and here at this end, I got my maximum compression. And that's exactly what this picture was starting to show us is if we flip the signs around. So here are the assumptions that we're going to make. Okay, just like with the other lateral methods, one is that this structure is subjected only to lateral loads. Okay, there can be no significant vertical loads acting on this. That the columns are roughly the same stiffness. Now, this method, they don't have to be located at, equal spans. They can be varied somewhat. Okay, that the structure is a flexible system for a tall beam, for a tall building. In most buildings, that's what they're classified as. Okay, and what we're going to do then is that if that is all true, then we're going to be placing, and that there is an inflection point then that is going to exist at the mid-height of the column and the mid-height of the beam, just like we did back in the portal method. Okay, it's exactly the same. So if you need some review on why that was, you can go back to our other video on the portal method and that'll explain it to you. Okay, on each story then, the axial loads in the columns are proportional to their distances from the centroid, or in this case the neutral axis of the pattern. So the hardest part is figuring out where is that location at. All right, so let's take a look at an example. It's very, very simple once you get into it, and so we'll go fairly short. Now, typically we do this for tall structures. I'm going to, just for the sake of keeping the calculations brief, we're going to do it on a short structure, and it won't be exactly right, but it'll be pretty close for a rigid structure. Okay, that we want to find then the axial forces, the shears, and the moments in the entire system. Okay, now the one assumption we do have to make is that the column sizes are roughly approximately the same, and so if I do that, we can come in and we have a structure that looks something like this. It's kind of a multi-story double portal. It has 30 feet for this span and it has 20 feet for the next span. the first story height is 16 feet and the top story height is 12 feet, and we have a value of 10 kips as a horizontal load acting here at G and a 20 kip horizontal load here acting at D. All right, so the methodology says the following. It says, first off, you go in and you put hinges everywhere. Okay, so mid-height of every story, so at 6 feet down from the top there's a hinge, 6 feet up from that floor is a hinge, and then we go to 8 feet down to this one, and then 8 feet up is this one. And so at mid-height of all the columns, that's where the hinges go, and then at the mid-span of all of the beams, you also get hinges as well. So at 15 feet, there's one here and one here, and then at 10 feet, there's one here and one here. Okay, so that's our basic structure. It looks exactly like what we did with the portal method. Okay, so that's how we're going to install our hinges. Okay, now what we're going to do is we're going to cut sections through the beams that basically go through these hinges at the mid-height of each story. Okay, and we're going to start at the top of the structure and we're going to work our way down. Okay, first thing we do is we solve for the centroid of the column area. So if all the column areas are the same, we know that from statics, our centroid calculation looks like this. That the centroid location measured from a reference is equal to the sum of all of the areas times their distance from the reference divided by the total area. Okay, so if we look at this, let's just call the reference here at this location. Okay, that we have a column that is located 0 from the reference, so that's a times 0, that's this value. Okay, the next column is located out at x equals 30. Again, measuring from this to this point here, so we have an a times 30, and then the other column that we have is a times 50 is located here. Okay, so it's 30 plus 20 gets me the 50 for him, so that's this term. And then in the bottom, we know that we had 3 a's that we were counting for. And if I do that, then the centroid is found to be at a distance of 66.67 feet. And that is not right. Let's try 26.67. Sorry about that. Okay, 26.67. Get that number a little better written. Okay, 26.67 feet to the centroid location, or what would be the neutral axis of this beam cross section. Okay, so now we're going to take our beam and we're going to look at just the top floor and work our way down. So here's the free body diagram. Okay, and we know that if I cut it at the hinges, there is no moment at the hinges. That's why we put it there, and so I have 2 reactions at each hinge. Okay, and then I have my 10 kip force on this point. The other one doesn't show up because it's on the piece down below. Okay, and then we know that my x bar is this dotted line is located 26.67 feet, which means that from here to here is 3.33 feet, and then it's another 20 feet to this one. And so if we assume that the forces are distributed based on their distance from that line, then we get kind of a diagram that looks something like the following. That there is a lumped value here that is in tension in that column, and so that lines up with this. So that's a tension in this column. My neutral axis was coming down through that location, and so on this side, I'm now getting a compressive force that's a lot smaller in this guy because he's closer to the neutral axis than the others. And then down here, I also get another compressive force on those. Okay, so this is the bottom of column QAF, and this is the bottom of the column. My labeling is off. If we come back and look, it's QDG is this is the bottom one. Yeah, so QDG is this guy. It is QEH is this one, and then FI is the last one. And so that's what we have on all of these. Okay, so then all I have to do to figure out what the values are is basically use similar triangles to solve for the relationship. So the first thing I'm going to do is that I'm going to sum moments, in order to be able to build up our particular values here. So what we do is we can say, all right, well, let's take a look at QEH, which was this little guy that was here. And if this whole length is 23.33 feet, okay, that I can write QEH's value in terms of this one as being this height to 3.33 is the same as this height to 26.67. That's what this ratio is. And so now I have QEH written as 0.125 times QDG. Okay, number 2 is QFI. And so this guy is now 23.3 feet away, so this is to 23.33 is the same as this guy is to 26.67. And so you find out that QFI, this one, is 0.875 times QDG. And you notice that I write them all in terms of one of them. Okay, so I have a QDG here, and then I have a function of QDG and a function of QDG. All right, so what I'm going to do on this is I'm going to sum moments, and I chose to sum moments on this about point J, which would be this hinge here. Okay, and what I get then is that I get, relative to this free body diagram, I now get 10 kips times that 6-foot dimension, because that hinge was put at the half height. Okay, and then to counter that, I get QEH multiplied by 30 feet, but we have an expression for QEH in current terms of QDG. Okay, and then I also get another 30 feet, or sorry, 50 feet to get out to the outer one, and it's multiplied by that value, which we also have a function for in terms of QDG, this guy. All right, now, when I go through and I do all that, notice that I summed this point here because it knocks out all of the unknown shears across the columns. Okay, in this particular example, we cannot do the portal method technique where we did V or 2V on those. We can't do that. So we're, in this method, in the cantilever method, we're going to solve for the axial forces first, and then we'll come back around and start solving for the rest of the pieces. So that's where this moment equation is doing for us. Okay, and that's then the reason that we chose to sum it at J is so that we could cancel the column shears at the bottom. All right, so that's my basic expression, and then we can substitute pieces in, and that's all I've done. And if you go through and you solve for this, you can find out that QDG is equal to 1.26 kips of tension for this particular structure. And if that's 1.26 kips of tension, then QEH, we said, was 0.125 times that value, so that gets me 0.16 kips. Now, obviously, for a real structure, these are very, very small values. You know, part of that is because the columns are so far apart. It's a very, very small calculation. All right, and so then my QEH is 0.16, and it was to the right. It's got the opposite sign, as we saw from this. So if this is tension, and this one is compression, as well as this one. So we'll come up with our value, and then I'll manually put the sign on this thing as being compression. And then do the same thing for QFI. It is 0.875 times that QDG value, that it becomes 1.1. Okay, and if you do all of this right, if this is positive and these are negatives, if I sum all those together, you better get 0, because that's the sum of forces in the Y equation. And that's exactly what happens, so we know equilibrium is balanced. But it's very, very easy to do this. Once I have the axial load, then I can go in and I can start to blow the structure apart into the pieces like we did the last time. Okay, now that was the axial load in the upper piece. Okay, what we're going to do is we're going to go in and we can repeat the process for the lower piece. Okay, but again, you take everything from, so for the second story, we go down to the hinges in the bottom floor, and now we have our free body diagram. And again, we're not cutting anything up above, we're keeping it all together. I now have the 10 kip load, but I also get the 20 on this, and then that's an 8-foot dimension here, and then you repeat the exact same process. And so when you sum moments, what changes is that you get the minus 10 times now what would be 20 feet up, and then I get a 20 times 8 feet gets me this guy, and then all the other terms are exactly the same. And then you can find out that the axial loads in these lower floors are actually something a little bit different, and you solve it the exact same way. So you can find their values have increased rather significantly because of all the loads. But that's it. That's all there is to the basic technique. Once you have that, then you can go back and play kind of the portal method game. That, well, all right, so I've got, you know, for our particular values, if we go in and start looking at analyzing the girders and whatnot, we can look at, you know, well, here's my girder going across the entire dimension of GH. So again, GH would be this beam here. So if I cut it just to the left of G and just to the right of G and just to the left of H, that's my beam, and I would get a moment and a shear at this end and an axial load, and I get a moment and a shear at this end on it. And so now you can start to set up your pictures, and I can come over to this joint, and I can come in and I can look at establishing this picture, and you can just work your way through this exactly the way that we've done all of our approximate methods before. And so I can find the shears at the end of the beam, I can find the moments at the end of the beam, and so forth and so on. Okay, and that's the way that you work it. So it's no major challenges at that point. The hardest part is finding the centroid and then finding the axial load, and then we can come in and start blowing things apart at the hinges to get all of the other unknowns. So it's pretty easy. So I'll leave this kind of as an exercise for you to kind of look at. But basically, we're going to sum moments about the hinges in order to calculate end moments on the beams. Okay, and that's kind of the trick. But you've got to go story by story. That's the trick on this one. All right, that you do start at the top and work your way down, and as you work your way down, you find out more and more information, and you can find out everything that you need to know. So I hope that's made sense to you. Again, it's a fairly quick technique for the approximate method. I don't use this one a lot just because the general requirement that it has to be a tall structure and a flexible structure means you have a lot of steps to go through. But in a pinch, it works, and it's kind of an interesting approach. So this method, the approximate method for the cantilever method or the beam analogy method, is you find the axial loads in the columns, that's the trick, and then use that to find the shears. Whereas in the portal method that we saw last time, you were using lateral loads and finding the shears in the columns and then using that to find everything else. So it's a little bit different. It depends on what you're after, but it's in a pinch, it works pretty well. So anyway, I hope that's been clear to you. As always, if you've got any questions, leave us some comments down below. We'll get back to you. And if you found the video to be useful or helpful at all, please toss us a like or a subscribe, and we will see you guys next time with more approximate methods. So happy engineering.